This video will record properties of definite integrals and also the definition of a definite integral. Before, we just talked about indefinite integrals. So, for instance, an indefinite integral would just be what is the integral of x squared dx. So the integral of that would just simply be 1/3 x cubed plus c. So that's called an indefinite integral. That means it's not definite. You have this plus c that's going on, and it's a function of x still. So what a definite integral is something that is actually going to be a value that we can find. It's like we're evaluating a definite integral. So the definition of the definite integral from a to b. So now we have a integral that we're looking at from a to b. Our x values is defined as the integral from a to b of f of x dx. So again, that would be called the integral from a to b, and a and b are x values. So the definite integral of a function is related to the area bounded by its graph and the x-axis. And that is something important to note. It's bounded by its graph and the x-axis. So if it's above the x-axis, then that's okay. It's just between the x-axis and then this function. But if it dips below the x-axis, then we have to adjust that, because then you get into negative area. So today we're not actually going to evaluate analytically, like using our math equations to evaluate definite integrals. We're just going to do them geometrically today. So we talked about a Riemann sum, and a Riemann sum is an estimate of a definite integral. Since the definite integral represents the area under the curve, the Riemann sum was an estimation of that. So some functions we can actually find geometrically because the shapes of their graphs lend themselves to geometric shapes that we know how to find the area of. For instance, linear functions. So if we look at the function 8 minus x from 0 to 8, so I'm going to graph this function. So 8 minus x has an y-intercept of 8, and then it will also hit the x-axis at 8, and then we have a negative slope of 1. So what we're finding is the area under that curve from 0 to 8, so 0 is here, under the curve and the above by the x-axis. So it's just this shape right here, which you can see is a triangle. So the area of this triangle is 1/2 base times height, or 1/2 times 8 times 8, which is 8 divided by 2 is 4. 4 times 8 is 32. Okay, so that is a definite integral. We just evaluated our first definite integral, and that is the exact area under the curve because it is a geometrical shape. Okay, so for part B, we have the square root of 25 minus x squared, which, just to remind you, that is a half circle. So remember, a circle formula is x squared plus y squared equals r squared. So then if you were to solve for y, you would get the square root of r squared minus x squared. And we're just looking at the positive side of this square root, so that it's a function. It passes the vertical line test. So this would be a circle with radius of 5. So let's draw this out. All right, so that's what our graph would look like. And then we're only finding the integral from 0 to 5. So what that means is we're only looking at the area under the curve in the x-axis from 0 to 5. So we're just looking at this piece right here, okay, which is a quarter of a circle, which we know how to find geometrically. So a quarter of a circle would be 1/4 pi r squared, and the radius is 5. So this would be 25 pi over 4, and that's the both the area under that curve and also the definite integral. Okay, so now that we understand what a definite integral looks like, there's some properties of definite integrals that we need to make sure and understand. So the first thing is, if I take the integral from a to a, if I take an integral from 0 to 0 or from 5 to 5 of the graph, that is no area. There is no width, so then the area will be 0. So the integral from anything to itself will have no area, so 0. Now the next thing is the integral from a to b is equal to, if I flip, so if you notice here, the a and the b are flipped, So if I flip a and b, then what happens is that means you need to multiply your integral by a negative. Okay. So just to give you an example of that, if I set the integral from 5 to 3 of f of x dx, whatever is here needs to be the lower number, and whatever here needs to be the upper number. Okay? So if whatever in the bottom is bigger than whatever is in the top, then what we need to do is we need to flip them so that we can find the area from 3 to 5 of f of x. But then when I do that, that area changes sign. Okay? All right, so some more properties we have. Number 3, if I find the area from A to C, and then find the area from C to B, and let's assume that C is between A and B. So let's say we find the area from A to C, and then another color, let's say, then we find the area from C to D, then all you have to do is just simply add them together. So then that would be the integral from A to B of f of x. Okay? All right, if you have a constant, k is a constant, and you have a constant inside your integral. This is a constant, not a variable. You cannot do this with x. Then you can take k outside of the integral and say that's it. All right? Next, just like with derivatives, if you are adding or subtracting integrals together, or functions together, and then taking the integral of that, then you can add or subtract the separate integrals from each other. As long as they're on the same integral, you can do that. So it's just basically saying that you can take the integral of each separate piece as long as they're being added or subtracted. If you are multiplying or dividing, you cannot do that, and there's special cases for that, which we'll talk about later. Okay, so example 2. Now that we're given some of these, now that we know these properties, we're given some information and we need to evaluate. These are certain types of problems that are on the AP test. Make sure you know these properties. So the first one, we say that the integral from 0 to 3 is 4, and then the integral from 3 to 6 is -1. So find the integral from 0 to 6. So this is the property that said if from integral from A to B plus the integral, or sorry, A to C plus the integral from C to B equals the integral from A to B. So this is going to be 4 plus -1, which is 3. Simply add those two integrals together. Now for part B, we have the integral from 6 to 3. 6 is bigger than 3, so that means we need to take the negative integral of 3 to 6, which is negative of -1, which is 1. For part C, that's easy. Integral from 3 to 3. Integral from 3 to 3, where'd it go? There it is. It doesn't matter what function it is, it will be 0. And then finally, the integral from 3 to 6, our numbers are okay, my integral is okay. I need to pull out the -5. That's the constant. So then the integral from 3 to 6, they tell us, was -1. So that is -5 times -1, which is 5. Okay, and a note real quickly here that I should have gone over. Go back to the first page, and I just want to make sure we understand A and B. Those are called the limits of integration. So if I ever refer to the limits of integration, it's talking about those integrals there. All right, so a couple more. If we are given a graph of f, we don't have a function for f, but we're given a graph of f that is all geometrical shapes. So here we have a horizontal line, then a diagonal line, and then half of a circle. So those are all shapes that we can calculate the area of geometrically. We don't have an equation of f yet. We're just looking at this, finding the definite integral geometrically. So if you were to find the integral from -3 to 2, so -3 is here, and 2 is here. So I'm looking at the area of that to that. All right. So this first area here is a trapezoid. and then this area here is a quarter circle. All right, so the area of the trapezoid, when we talked about trapezoid Riemann sums, hopefully you remember that, is 1/2 base 1 plus base 2. So this time, this trapezoid, you've got base 1 here, base 2 here, and then here's the height. So base 1 has a length of 1, base 2 has a length of 3, and then times our height has a length of 2. So that's the trapezoid. Now something else we want to talk about this trapezoid falls below the x-axis. So if a function falls below the x-axis, and its whole area is below the x-axis, that means that that area is negative area. So it's kind of like if velocity is negative, then we're moving in the opposite direction. So we still have a total distance there, there's still an area there, but it's going to be subtracted away from the total area. All right, so so watch out for that. So that's under the x-axis, under x-axis, therefore negative. Okay, then we have our quarter circle, which is above the x-axis, so it will be positive. So that's going to be 1/4 pi. R is 2 squared. All of that together, that would be 4 divided by -2 is -2, -4, plus pi is the area represented there. Okay? So now for part B, the integral from 4 to 0. Off the bat, we should see 4 is bigger than 0, so we need to go ahead and correct this. This is going to be the negative, or the opposite of the integral from 0 to 4 of f of x dx. So from 0 to 4, here's 4. So we're finding just this entire area here of the semicircle. So that is above the x-axis, but since we had to flip our sign, then the area is actually going to be negative. So it'll be the negative half of the circle, pi r squared, or just simply negative 2 pi. All right? And the final one, the integral from -4 to 4 of f of x plus 2. Now, from -4 to 4, this is the entire interval. So we're finding all of the area this time. But we have something else different here. We have this plus 2 here. Does that mean that you can find this whole area and then just add 2 to it? No. This does not equal the integral of f plus 2, like that. Does not equal that. You cannot take that constant out. Okay? So make sure you do not do that, because I have seen that before. The 2 is still need to be integrated. So using our properties of integrals, we can say that this is the integral from -4 to 4 of f of x dx plus the integral from -4 to 4 of 2 dx. Okay? Just because 2 is a constant, you still have an integral, because the integral of 2 is 2x. So that does exist. Now, if we think about this graphically, that means we're looking at the graph of y equals 2. So the graph of y equals 2 from -4 to 4, that's just a horizontal line. And from -4 to 4, we just have a regular rectangle. Okay? So that does have area, it's not just 2. So the integral from -4 to 4 of f is going to be this trapezoid here. Falls below the x-axis, so that's going to be a -1/2 times a width of 2. Base 1 is 2 plus base 2 is 4. Now, we already calculated that the area of the semicircle was 2 pi. But for this problem, it's now going to be positive, so we're going to add on 4 pi. Then we're also going to add on the area under the curve of y equals 2. That has a length of 8, a width of 2, so that's going to be an area of 16. So to calculate this, it's -6 plus 4 pi plus 16, or 10 plus 4 pi. Okay. So again, we have not done this analytically. On the next lesson, we're going to evaluate definite integrals, not graphically, because obviously you cannot solve the definite integral of every function graphically.